Hi, in this video I'll be covering problem number 7. So you have to find all the zeros. The first one given here is a cubic function, so I've typed it in the calculator. Remember, your steps are to first identify any real rational roots. So when we graph this, we see that it crosses at -2. So I know that x equals -2, but that the other two must be imaginary because we don't see where it crosses the x-axis. To get started, we put our 0, -2 in a box and we do synthetic division. Be sure to look and make sure there aren't any missing terms that you would need to add 0 terms in for. So we have 1, 2, 16, and 32. Remember, if your math is correct, because -2 is a 0, your remainder should come out to equal 0. 1, -2, 0, 0, 16, -32, 0. So we go from x cubed and decrease by 1 exponent, or 1 degree, so that'll be x squared. There's no linear term, and it's equal to 16, or plus 16 equals 0. From here, we subtract 16 from both sides. X squared equals -16. Remember that you are supposed to get two imaginary roots, so it should make sense that we get plus or minus 4i. So I'll list 4i and -4i as our other solutions. For number 8, you've got to find all the zeros for 4x cubed plus 5x squared minus 36. We can get an idea of what those zeros look like by graphing, or the number and types that we have. And it appears to cross here at -2 and +2. We can verify that on our table because we see -2, 0 and 2, 0. So we know that 2 of our answers are given by the graph. And we can either do division or we can factor this. I'll show you both ways, but for the remainder of the ones that are factorable, I'll be factoring. So if we start off with 2 and we put in 1, we're missing a cubic term. We're missing a linear term. So 1, 0, 5, 0, -36. 1, 2, 2, 4, 9, 18, 18, +36, 0. And then we divide again with -2. 1, -2, 0, 0, 9, -18, 0. And we get x squared plus 9 equals 0. Subtract 9 from both sides. Remember, the other two are imaginary, so we have positive or negative 3i. And we're through. Now remember, we can also verify these by just making sure, well, I guess you can't really verify, but just make sure you at least have your real ones and know that the other two are imaginary. Next, for C, you are asked, this was B, not 8. For C, you are asked to find all the zeros, but if you take a look at this one, guys, it's quadratic. So if we graph this to see what they look like, we should know that we only have 2 zeros. But if you saw it graphed a little something up here, I'm going to increase my y max to 20, see what's going on. Oh, we see that it doesn't touch the x-axis, so that tells us we have 2 imaginary roots. So that means we have to use either completing the square or quadratic formula. I'm going to go ahead and use quadratic formula, but the first thing I always do is find b squared minus 4ac, our discriminant. Our b value is -5, our a value is 3, and our c value is 12. So in my calculator, -5 squared minus 4 times 3 times 12, get -119. So x is equal to the opposite of b. So that'll be, if b is negative 5, the opposite of b is positive 5, plus or minus the square root of negative 119, all over 2 times a, which is 3. So x equals 5 plus or minus. Now 119, it looks like it's prime. If you were going to try to find a common factor, you would want to try one that was odd. It adds up to 11. Usually that's a prime. And unless 11 is a factor, it's prime. So if I try to divide by some odd number, I get 7 and 17. So it's not prime, but I don't get any pairs because 7 is a prime number and 17 is prime. So that means I cannot reduce it any further. And that would be my answer. So our two answers we have here are 5 plus I square roots of 9, or I square roots of 119 over 6, but it is totally acceptable, oops, let me put my I in there, to put it all over 6, like that, and not separate them, okay? Plus or minus is fine. Next, I'm going to try factoring on D because I noticed they have a GCF. Let's see, C, D. So 3x to the 6 minus 3x squared equals 0. If I pull out a common factor of 3x squared, have x to the 4th minus 1. Oh, good. We should see here that this is a difference of squares. That factors into x squared minus 1, x squared plus 1. And if we want, we could go ahead and set the factors equal to 0 and solve, but I'll go ahead and continue to factor this difference of squares, the x squared minus 1, into x minus 1, x plus 1. Well, I guess we could, by the way, go ahead and graph it. 3x to the 6th minus 3x squared zoom 6 and we have, it looks like 4 that are real, okay? And if we want to zoom in a little bit more and see what's going on here, we're at the zeros. Let's take a look. 1. Well, we can see really well what behavior is going on. You can see here that it crosses at -1 and +1, but it bounces off at 0, so we've got an even multiplicity, which should make sense because of this factor here. If we set 3x squared equal to 0 and solve, we would get that x is equal to 0, but its multiplicity is 2 because it's squared. Here we get +1, -1, and if you set x squared plus 1 equal to 0 and solve, taking the square root of both sides, we get x is positive or negative I. So our answer here would be 0 multiplicity 2, positive and negative 1, and positive and negative I. And that gives us a total of 6 zeros. Remember, if we have multiplicity 2, that 0 counts as 2 solutions. Okay? Next, we've got E, and if you take a look at it, that should be one that we could do by U substitution. It also is factorable, so you don't have to use U substitution. If you think about it, the way you can think through it and see if it's factorable, what factors of 63 could combine to give us 2? 63 is a product of 9 and 7, so you could make 9 and 7 equal 2. I am going to go ahead and use U substitution, however, and define U as x squared, making it U squared minus 2U minus 63 equals 0, giving us a simple quadratic here to solve. That would factor into U minus 9 and U plus 7. So U equals -7 and positive 9. Then we go back and substitute what U represents, which is x squared. And I want you to think real clear and think about whether if you square a number, you can actually get a -7. Can you square a number and get a negative 7. So in this case, I guess we could have taken a look at our graph here. X to the 4th minus 2x squared minus 63. If we graph it, oops, let me hit zoom 6. It does appear to cross here at negative 3 and 3. We got to take the square root of both sides, right? So can we take the square root? Let me see, I'm sorry. Let's go ahead and do this then. So x would equal, if you go ahead and solve it, plus or minus I square roots of 7. I'm writing it wrong. Equals plus or minus I square roots of 7. And here, x equals positive or negative 3. So we should see it cross at positive 3 and negative 3. And we also, which tells us that 2 of our roots are real, 2 of our 4 are real, and 2 are complex. So this should make sense that x squared is equal to I square roots of 7, because that gives us our imaginary solution, okay? So for E, again, that's x equals positive or negative 3 and positive or negative I square roots of 7. Now, if you wanted to, you could, of course, avoid factoring altogether and use 3 and negative 3 to do synthetic division. You would still end up getting a depressed quadratic that would solve to give you plus or minus I square roots of 7. All right, moving on to F. Let's go ahead and look at the graph. I should have 4 solutions total. And it looks like it crosses at 0 and 2. So let's check that out on our table. And in fact, we can verify that 0, 0 is on our table and 2, 0 as well. So we know that x equals 0 and 2, and that we are going to have 2 imaginary roots. So if I solve this, I can use 0 and do division, and then 2 and use division, do division. I'm going to notice that they have a common factor of 4x, leaving me with the quantity x cubed minus 8. Hopefully you recognize this as a difference of cubes. So by the way, this is the factor that gives you the 0. So we know x equals 0. And this factors into a sum, or excuse me, a binomial times a trinomial. Our sign pattern is minus, plus, plus, cube root, so x and 2. Square the first term, multiply, square the last. So that's where we get positive 2. If you notice, x minus 2 equals 0, so x equals 2. So that's where we've just proved these two. Now we get this factor x squared plus 2x plus 4. So if you did long division with 0 and 2, the depressed quadratic would be x squared plus 2x plus 4. So now we just want to take this and solve it for x. So we know that they should be complex zeros, so we need to either use completing the square or quadratic formula. Because this is even, I'm definitely going to use completing the square. Because I can take half of 2, which is 1, square it and get 1. When I factor, x plus 1 quantity squared equals negative 3. Take the square root of both sides. And then subtract 1 with a final set of complex zeros of negative 1 plus or minus I squared roots of 3, imaginary zeros, okay? So there's all 4 of my solutions found algebraically. Hopefully you see that all this really can a lot of times be done without ever looking at a calculator. So I've got negative 1 plus I squared roots of 3 and negative 1 minus I squared roots of 3. But of course you could write it together as negative 1 plus or minus I squared roots of 3.